Walking is impressive, but grasping remains the true bottleneck for humanoid robots. While we celebrate machines that can navigate complex terrain, the moment they attempt to interact with the physical world, the illusion of human-level autonomy shatters. The reality is that dexterous manipulation is not merely a difficult challenge, it is the critical mechanical failure point preventing widespread deployment. By the end of this explanation, you will understand exactly why current rigid hand designs are fundamentally broken and how a shift towards soft robotics and isomorphic control loops is the only path forward. For years, the robotics community has treated locomotion and manipulation as separate problems. We have poured resources into making robots walk, run, and balance, and the results are undeniable. We have reached a state where walking is nearly solved. A robot can traverse uneven ground with a stability that would have been science fiction a decade ago. But here is the thing. That same robot, when asked to pick up a fragile object while standing, often fails catastrophically. The gap between these two capabilities is not a minor calibration issue. It is a fundamental disconnect in how we design and control these machines. The primary mechanical bottleneck is not a lack of actuator torque or raw power. Modern joints can generate more than enough force to lift heavy loads. The problem lies in the coupling of high-dimensional dexterous finger dynamics with whole-body balance. When a robot attempts to manipulate an object, it must manage conflicting forces simultaneously. The fingers need to apply precise, variable pressure to grip a shape, while the entire body must maintain stability against those same forces. Current rigid body models cannot resolve this control space. The mathematics of simultaneous locomotion and manipulation creates a state of instability that traditional control architectures simply cannot handle. Consider how we currently operate these machines. Most systems rely on teleoperation, where a human operator controls the robot remotely. This approach seems like a logical bridge to autonomy, but it actually exacerbates the problem. Inverse kinematics, the math used to translate human hand movements into robot commands, introduces retargeting errors. The robot cannot perfectly map the fluid range of motion of a human hand onto its own rigid mechanical structure. This forces the operator into limited, unnatural postures, such as squatting, just to maintain a stable base. The disconnect between operator expectation and robot execution means that what feels natural to a human becomes a struggle for the machine. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The fragility of these complex machines is another hidden cost. We are building systems that are incredibly sophisticated but mechanically brittle. Rigid robotic hands suffer from catastrophic failure modes in unstructured environments because they lack compliance. They cannot absorb impact or adapt to object geometry without complex real-time sensing that is often too slow to prevent damage. If a robot tries to grab a box that is slightly larger than expected, a rigid hand might crush it or slip entirely. The lack of passive deformation means every interaction is a high-stakes calculation. This brings us to the emerging solution. The path to true dexterity lies in soft robotics and exoskeleton-based interfaces. Researchers are now exploring systems that combine isomorphic controls with reinforcement learning. One notable project, the Humanoid cockpit, allows operators to control a humanoid robot using an exoskeleton that mimics human hand and arm movements. This system uses variable stiffness and passive deformation to absorb impact. The soft materials adapt to the object's shape before the robot even applies force, reducing the need for complex sensing. However, the transition to this new paradigm is not instantaneous. The architectural trade-off for dexterous manipulation requires shifting from centralized high-level planning to decentralized isomorphic control loops. We're moving away from a single brain trying to control every joint and toward a system where local controllers manage specific dynamics while maintaining overall balance. This shift allows for the conflicting dynamics of locomotion and fine manipulation to coexist without collapsing the system. But even with these advances, the timeline for adoption is complicated. Industry perspectives suggest that while narrow AI has improved sensory capabilities, true functional intelligence for unstructured environments may require a decade rather than the projected 2 to 3 years. The reliance on high-quality human data for imitation learning creates a significant knowledge gap. Current foundation models struggle to generalize dexterity across the vast variety of unstructured objects found in real-world settings. We can train a robot to pick up a specific coffee cup, but the moment the object changes shape, texture, or weight, the system often fails. Current benchmarks for humanoid success are skewed towards static or pre-programmed tasks. These tests mask the fact that the grasping gap is actually a failure of adaptive force control in dynamic, non-deterministic environments. Until soft robotic hands can match the robustness of human skin and the control systems can seamlessly integrate tactile sensing with whole-body dynamics, grasping will remain the primary barrier. The hardware is improving, but the software and the fundamental control philosophy are lagging behind the hype. We are seeing the first signs of this shift in research. Papers from RxIve highlight that while locomotion has reached a near-solved state, the integration of manipulation remains the critical challenge. The emerging solutions suggest that we must stop trying to force rigid hands to behave like human fingers. Instead, we must embrace the chaos of soft materials and the complexity of whole-body dynamics. The future of humanoid robots does not lie in making them more like machines. It lies in making them more like biological systems that can adapt, deform, and recover from error in real time. The road ahead is long. We are moving from a world where robots can walk but cannot touch to a world where they can do both. But this transition requires us to abandon the rigid models that have dominated the field for decades. It requires a new understanding of how to couple the delicate art of grasping with the brute force of locomotion. The engineering challenges are immense, but the potential reward is a level of autonomy that could transform every industry from manufacturing to healthcare. Until we solve the grasping gap, the promise of the humanoid robot will remain just out of reach. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.